Okay, so here's a collaborative problem dealing with power. And we've got a load to the right of my two dots here, which has got a 6 ohm resistor with a capacitor and another resistor in parallel. And the question is, we've got three questions. The first is find the power factor of the load as seen by the source. Don't just tell me the power factor, but also include whether it's leading or lagging. Second question is to find the apparent power S delivered by the source, include units. And then the last question is to find the average power delivered by the source. Similarly, include units. So my challenge to you is to, if you're watching this on video, to pause it now and see how far you can get with those. DJ, since you're with us, I'm going to ask you.
Yes.
If I asked you for what the apparent power being dissipated by this 4 ohm resistor, or this apparent power being dissipated by this capacitor, or the apparent power dissipated by those two in parallel, I need to find the current through them. I need to find the voltage across them. And then once I knew the current through them and the voltage across them, I could then start to use these equations, the equations at the bottom, to figure out my average power and my apparent power and my power factor. But since I'm asking for just the entire power delivered to the entire load, I'm going to simplify this load. So tell me the equation for the simplified load.
10 minus J2, because the capacitor and resistor in parallel. So you would do the
That's it. 6 plus.
6 plus. I'm trying to do the math for that.
Oh, let's just write it down. 4 in parallel with minus J2.
Okay. Yeah.
How about making it simple? And we know that it's product over sums, right? So give me the product.
4.
The product of 4 and minus J2. What's 4 times minus J2?
8 minus 8.
Minus J8 all over the sum, which is what's 4 minus J2.
Yes.
I wouldn't mess with that. I just throw that in the calculator and see what the calculator says. It's a impedance. So we're going to write it in rectangular form. 6.8 minus J 1.6. Whenever we want to talk about what power is, whether apparent or anything else, or average or power factors, the first thing we want to find always is the voltage across it and the current through it. And we already know the voltage across it. The voltage across it in RMS is equal to 30 at an angle of 0. Same thing, it's just plain old 30. Now we can figure out what the current through it is. And DJ, what is that?
Wouldn't it be so I equals 30
right.
over whatever your resistance is or your impedance?
That's it. So it's 30 at an angle of 0 all over 6.8 minus J 1.6. It's a source, so we're going to write it in polar notation, and that's 4.29 at an angle of 13.2 amps. The calculator just does that for us. And now armed with these intermediate answers, armed with this intermediate answer and this intermediate answer, let's answer the question about what is the power factor? What's the formula for the power factor coming out from our first page?
Sorry, it's the cosine theta. What is it? Which one is it? Is it theta?
Does it matter which comes first?
No, it doesn't.
So that's easy. So put either of them first. We always want to measure phases relative to voltage. So maybe it kind of makes sense to put the voltage second. So in this case, it would be theta I, which is,
oh, sorry, 4.9, or is it 13.2?
you tell me which one it is. Which one is it?
13.2.
13.2 minus
0.
So that gives us the cosine of 13.2, and that is equal to 0.973. Again, thank goodness for calculators. But now we need to say whether or not it's leading or lagging.
So now we have to compare them, and if is it the
Well, remember, we're comparing theta I to theta V, and theta I we said is 13.2, and theta V we said is 0. So which is bigger?
leading theta I?
So it's bigger. So since theta I relative to the voltage is in front, is bigger, we say it is what?
Leading.
Leading. And we know this section here. That's an important one to know. Since it's leading, we know the load looks capacitive. Let's just check it out. Does that load look capacitive? Does this load look capacitive?
Yes.
Yeah, it does. It's got a negative imaginary part, so it does look capacitive. So we're pretty sure that this is the correct answer. All right, just two more parts, and these actually get much simpler. Find the apparent power delivered by the source. So we need to know what is the formula for S. Do you remember it, or should we go back?
IRMS
Yeah.
times V. This.
Yeah, that's it. So fill in the numbers for me. What's IRMS?
4.29.
Now, here's the question. Do we put in the angle or not to find apparent power?
No.
No. We're just putting in the maximum values, and VRMS is 30, just the maximum value, and that turns out to be 129. And what are the units?
I forgot.
Volt amps. It's like they couldn't come up with a new.
Oh, that would make sense giving. Okay.
Yeah, sort of. But it also would sort of make sense calling it watts, but they want to make it really clear that this is not an average power and it's not an instantaneous power. It's this weird thing called apparent power, which is neither. Nothing is really burning up 129 units of power of anything. It's 129 units of power that are being shuttled back and forth on the power lines. It's much less actually average power that's being used. That's the next question is, of that 129 volt amps, how much is the actual power being used? What's the formula to find actual power as a function of S and PF, as a function of our parts A and B? Average power, S and PF.
So you take the two and just multiply them.
That's it.
So can we just take our 129 and multiply it by our 0.973?
That's it exactly. And you'll end up with 125. What are the units?
Volt amps.
No, not for average power. Well, oh, I'm sorry. I see what you're saying. 129, it's 129 volt amps times the power factor, and that gives you 125, which is the average power. And what's the units of average power?
I was gonna say volt amps leading but I don't think that's right.
So you're confusing two ideas. Leading or lagging, you only talk about that with the power factor. It's almost like the units of power factor. You talk about leading or lagging. It's a number followed by that leading or lagging. When we're talking about apparent power, that's going to be a single number, a scalar number, never a phasor. And then what are the units on apparent power?
Volt amps.
Volt amps. And then average power, same thing. It's always going to be a number. It's always going to be a scalar, never a phasor. And it's followed by the units. And the units of average power are just old-fashioned watts. So that's
okay. I see.
So that's it. And so those are our three answers. So big picture again, when you're doing these collaborative problems, anything to do with power, the question is going to say stuff about what's the average power or what's the apparent power or what's the power factor of some component. And the first way to answer those questions is to figure out what's the voltage across that component, what's the current through that component, measure both in volt amps, and then everything else just falls apart based upon the equations given in this first page, based upon apparent power, power factor, and then multiply them together to find the average power. And that's it.